Okay, good morning all. So this is the last part of our discussion, that is called quantization, and after quantization we will discuss with respect to PCM. These are the last two topics come into picture in our module 3. So now this quantization, already we have seen how this quantizer will work. The quantization means it will round up the particular sample value after a sampling process. So we have seen that after the sampling, if there is a quantizer, then the resultant, the whole thing will be called as a discretization. Okay, and it will help in our analog to digital conversion. So as we have discussed earlier, there are two basic block diagrams or two basic blocks. This is our sampler, okay, and this is our quantizer. Okay, so when I will provide x of t, the sampler will provide x of n. Then, and the sampling signal, which is either natural sample or a flat top sample, or if it is instantaneous. If it is instantaneous, no need to quantize, it is a quantized already. Only we have to identify the levels. Okay, so this quantizer resultant is x cube of n. Done. So this is the output of quantizer. Now these two steps, if I will consider, then these two steps is called as a discretization. Done. So depend upon this theory, we need to discrete the levels, we need to discrete the signals, and once it is discretized, how many number of levels we are going to identify, and with respect to each level, how many number of binary bits we are going to represent. That is our main motive. In the previous class also have discussed, when we are discussing quantization process, that quantizer will work on a quantizing levels, that is called levels. Okay, and this level is dependent on number of binary bits. Each level will be assigned with binary bits. So let first understand what is this level, then we will go to this particular picture. It is easy to understand. Okay. Now suppose if this quantizer is having a level of 8. 8 levels are there, means there are 8 levels in it. I will show how it is. Okay. So if it is 8 levels, so that means I can write 2 to the power 3 or 2 to the power n, so that n is equals to 3. So if n is equals to 3 means each level will be assigned with binary bit, 3 number of binary bits will be there. What are the binary bits? Suppose if it is L1, L2, L3, L4, L5, L6, L7, and this is L0. Level 0 is not considered. So if it is level 1, 0, 0, 1, if it is level 2, 0, 1, 0, if it is level 3, 0, 1, 1, if it is level 4, 1, 0, 0, and if it is 5, 1, 0, 1, if it is 6, 1, 1, 0, if it is 7, 0, 0. So these are the binary bits will be assigned to the individual levels, and according to that, the potential available in the discrete positions will be converted into the binary data. And once this binary data is converted, that means we have converted our analog signal into the binary data, and then we can transmit from a parallel to series form, because this all data will be available in a parallel manner. We need to convert into series. So parallel to series connection will be there, or converter will be there, which will convert and form as a bit stream, binary bit stream. Okay. Now come to this particular field. Now we will understand what this quantization actually. Let us consider this white line is my modulating signal. Let us consider this is modulating signal. Now I need to quantize this modulating signal. So what I do? So first step is sampling. Number of samples will be created. Second is quantizing. So quantization means identification of number of levels. Each level will be assigned with a certain binary data, and then it will be converted into a digital data. That is with the help of our encoder. Quantization is only in the round of value. Okay. If there is a sample, the round of value will be identified. Okay. Now how it is happening? Let's see. Now here you can see these fixed lines are called as decision boundary. Okay, decision boundary is always one number greater than the number of levels. Okay, and this decision boundary, within this only my maximum to peak amplitude is going to be available. As you can see, the modulating signal peak is Vn and the modulating signal lower potential is Vl. So this is our lower potential and this is our higher potential. So the decision boundary will differ according to the modulating signal amplitude. Okay, then next step, after determining the number of decision levels or decision boundary, these lines are called as this D1, D4, D3, D2 and D1 is called as decision boundary. Within this you need to decide that which particular level is going to assign to your quantized level. Okay, how? Let's see. So these all are the decision boundary. Now how to identify the levels? Next question. The depend upon the decision levels, if you subtract -1, you will get the number of levels. Now as you can see, these dotted lines are the mid position of the decision boundary between D5 and D4, D4 and D3, D4 and D3 and D2, then D2 and D1. This is the mid line. Okay, this mid line is used to identify the number of levels. So how many number of levels? As you can see, level 4, level 3, level 2, so level 1. So that means how many number of levels? 4 levels. Done. So how many number of decision boundary? Decision boundary is number of level plus 1. So number of level is 4, 4 plus 1 is 5. So this is my decision boundary. You can see D5, D4, D3, D2, D1. So these are the decision levels. And the levels are -1 to each particular value. So I can write D is equals to 10 plus 1. So number of levels is 4. So decision boundary will be 5. Over next. Now this is my modulating signal which I want to quantize it, which I want to sample it. After sampling, quantization is how we are going to do. Okay. Now if my particular modulating signal is in this particular range, means in a decision level, in a boundary between D1 and D2. Okay. Now in this, the quantizer will decide according to the levels, not to the decision boundary. It is according to the levels. How? So when this particular signal is within D1 and D2, the quantizer will identify from this particular level, from the midpoint, because it will identify the nearest value. Its nearest value to this, means suppose this is 2.5, let us consider this is 2.8 and this is 3. We will see all those later on. This 2.3 will be the level potential and it will identify this lower potential, means nearest potential it will identify, quantized value. Okay. So my step will identify or my signal will follow from this level to this particular level. Means when it is within this particular boundary or between decision 1 and decision 2, the total potential available within this particular signal, suppose this is our white line is within decision 1 and decision 2. First, if I am discussing with respect to 2. So my quantizer will follow this particular level. Means it will not consider this lower decision level. It will identify decision boundary. It will identify the level 1. Now once this level is identified, next the signal is entering the decision boundary 3. Okay. So now when it is entering to decision boundary 3, quantizer will jump to the next decision level as the signal is entering to the decision boundary. So it will enter to the second level. So it is entering to the second level like this. Similarly, when the signal is increasing from D3 to D4, your step size will increase. This is the quantizer. We will see how many types of quantizer. Okay, and that quantizer will depend upon the number of steps, or that step remain constant. So it will jump from level 2 to level 3. Similarly, the signal is moving from decision boundary 4 to 5. So it is jumping from level 3 to level 4. Okay. Now, if the signal means modulating signal, if it is coming back from the higher value to the lower value, again from the lower potential means at the level 4 now, you need to decrease to the level 3 because it is decreasing to the level 3. It will not follow this particular case, it will follow these pulses. So these particular pulses are nothing but quantized levels. Okay, quantized levels of a particular modulating signal. So these lines comes under your quantizer. The quantizer will come into picture when the number of decision levels are identified, number of decision boundaries are there, how many number of levels are there. According to that, the step size are identified. Now, here you can see I have written del. The distance between two decision boundary is del, and distance between two levels is also del. Del is called step size. Okay, this is called step size. Now, how to calculate this step size? The calculation is maximum potential available in the modulating signal minus minimum potential available in the modulating signal divided by number of levels. So here number of levels is how much? 4. So VH minus VL divided by L. So this I can write VH minus VL divided by 2 to the power n. Like this I can write, because L is nothing but 2 to the power n, where n is the number of binary bits. In this case, how many number of levels? 4 levels. So if the number of level is 4, that means it is 2 to the power 2. So each level is assigned with 2 binary bits. So 2 binary bits means how we will represent? L1, L2, L3, L4. Okay. Now if it is L1, I can write 0, 1. If it is L2, I can write 1, 0. Similarly, L3 means 4 possible combination. It is 0, 0, 0, 1, 1, 0, 1. So L1 you can represent with 0, 0 or any of these follow this particular combination. So these combinations are, as you can see, okay. So here it is 1, 1, then it is 1, 0, then this level will be 0, 1, and this level will be 0, 0. Because there are 4 levels. So 0, 0, 0, 1, then 1, 0 and 1, 1. Simple, only assigning the number of binary data. So binary data is identified with respect to the number of levels. So this is one level and this is one levels. So assigning these levels depend upon the number of binary bits. If the number of levels are 8, that means how many number of binary bits will come? The binary bit will come with respect to this sort of levels: L1, L2, L3, L4, L5, L6, L7, like that. So this is the quantization process. Now, for example, let us consider a point A at this particular point. Now, how it is decided? Which particular point we are going to identify? Now, suppose if my point lies at this particular case, at this particular point I am considering point A at the level 3. Okay. Now, if it is at level 3, the nearest potential available, or the nearest potential means if it is lies between this particular case, the decision level D3 and the level L3. If my potential lies at this particular point, so it will take the next nearer part. The decision will be done with respect to the next part. So the next part is what? This particular point will be identified as the nearest value. Okay. Similarly, now here there is a two choice. Now here either it will go to the up or it will consider this. If it is considered this output, that means potential will decrease. If it is considering the lower value, potential will decrease. So the difference will be same, because here the step is same. Here the step size is del by 2. Here also it is del by Done. Similarly, now if the point is at this particular point, okay. Now if this signal, if I am considering the point is here, so the nearest potential is what? Nearest potential is the potential available in the decision boundary 4. So it will consider this particular point. So like that, the number of levels will be identified. So if it is entering to this particular decision boundary, automatically it will take as level 4, because decision boundary 4 nearest value is the levels. So decision boundary is only the giving the level limitation. Okay. So level limitation will be identified with this particular variation. Now, when these particular points are identifying position to position, it is having two choices. But if it is coming at this particular end point, or if you consider at this particular point, wherever it is, if I am considering here, if the point is here, my choice is only to go up, not to the down, because there is no other level is available. So here, if the point is available in this particular range, it will consider to level 2. Similarly, if it is false in this particular region, it will consider level 1. So depend upon the nearest value, it will round up and provide the level binary bits. Okay. So this is the process called as a quantization. This quantization means round up to the nearest value, round up to the nearest levels, assigning the binary bits. Assigned binary bits will be the encoded of that particular level. Now suppose if I am giving, if my input to the quantizer, let us consider here, if my input to the quantizer is 2.8 volt, done, but the after quantization, the nearest value it is identifying as 3 volt. So it is round up to the next value. So round up to the next value, according to the quantizer, he will see that 3 volt is assigned to which particular level. So it will assign to that particular level and assign the binary bits depend upon the number of levels. So if the number of levels is 8, that means automatically this 3 will be assigned with that particular binary bit and it will be encoded by the encoder. If the next time if I will draw with encoder, then whole system it will become as an analog to digital conversion. Okay. So this is the basic steps behind our quantization process. But it is having certain features that I will note down now. So now we need to calculate this quantization error. Now what it is? Quantization error means it is a difference between input to the quantizer to the output of a quantizer. Okay, so that is an error. Why I am saying it is called error? Because I am providing 2.8 volt, but it is quantized to 3 volt. So what is the difference? The difference is minus 0.2 volt. So minus 0.2 discrepancy is there, that means some error is there. My actual potential is 2.8, but after quantization it is 3. So this is called as an error, and this error contributes to the noise, because quantizer is also contributing some sort of noise, and we need to calculate SQNR, signal to quantization noise ratio, as we have calculated SNR for different cases for AM, FM, DSP-AC, SSP-AC, for PM and all these things. Similarly, when we come into this pulse code modulation or this quantization platform, in this also some error is identified, and this error contribute to the noise, because I am providing 2.8 volt, but after quantization it is giving 3 volt, which is an error. It is an error, slight error. So how to minimize this particular error? That is our main motive. My quantizer must be so efficient that whatever I will give, it will quantize to the nearest value, so that the error will be less. If it is round up to the higher value, that means error will be more. For example, if my value falls in this particular region, if the quantizer identify the next level, that is L3 or it is within L2, if it is false in L2, error is very less, because potential difference is very less. But if it is false in L3, the potential difference is very high. because the difference between input and output of a quantizer is high, due to which discrepancy will be there. I am providing 2.8 volt, but if I am getting 4 volt, that means it is an error. It is an error with respect to what? Input with respect to the output. So if such cases are happening, that means we need to calculate the error, and that is called as a quantization error. So if I am providing 2.8 volt and output is about 3 volt, you can see the difference is very less. But if the output is 4 volt, then the difference is more. If the difference is more, that means it will identify as an error, and if it is an error, it will contribute act as a noise. So if it is a noise, that means I can consider this one to calculate SQ and R. SQ and R. What is SQ and R? It is signal to quantization noise ratio. Quantization noise ratio. So here which one is the signal? Signal is this. Which one is the quantization error? The difference between these two. If you take the power of individual component and if you take a ratio, then you will get SQ and R. And the concept what it is, our signal strength must be so better with respect to the noise, so that the signal to noise ratio will be less than, or it must be greater than 1, because signal quality must be high with respect to the error. If the error is less, for example, if I am taking this one, okay, so 2.8 and 3 is the output, so what is the error? So error is minus 0.2 volt, means 2.8 minus 3 is minus 0.2 volt. This is an error. So signal to quantization noise ratio, if I will calculate, signal power is 2.8 whole square and divided by 0.2 whole square. So here if you calculate it, you will get around 28 into 28 divided by 4. So this is 2, this is 14, this is 1 4. So 14 into 14, which is greater than 1. So like this, your value will change. Your signal to quality is greater than 1. If it is greater than 1, means your signal quality is good, because error component is less. Similarly, if I will take a difference of 2.8 and 4, near about 1.2 it will come. So it is more than this. Okay, if it is more than this, that means your signal to quantization noise ratio is less as compared to this particular case. So we need to minimize the error. Okay, the roundup must be so accurate that the same value can be extracted nearest. But if the value falls in the level 3 or it is falls in decision 2 and decision 3, and your output comes beyond this decision 5, that means there is a huge difference. If there is a huge difference, that means there is an error contribution is there, and that error is called as quantization error, and this is also called as noise. So we need to calculate this particular factor called signal to quantization noise ratio. There is some procedure that we will see. So maximum quantization error, as you can see, if it is falls within this two particular range, the difference is del by 2. Okay, but if it is falls in this particular range, then also it is del by 2, because step size remain constant between the levels and the decision boundary. So maximum quantization error, maximum quantization error is del by 2, because that is the half of the step size. Means the maximum error will be this much. This is the limitation of a quantization error. That is called maximum quantization error for a particular quantizer if it is a uniform quantization. Uniform quantization means, as you can see, the step size remain constant. This del remain constant throughout the levels, throughout the decision boundary. If it is not constant, then it will be called as a non-uniform quantization. So there are two methods are there. One is uniform quantization, one is non-uniform quantization. Whatever we are discussing, it is with respect to uniform quantization. So maximum quantization error in uniform case, it is del by 2. Next, what is the range of quantization error? The range of quantization error. So the range of quantization error is minus del by 2 less than q less than del by 2. What is q? It is q is called as a quantization. After quantization, here you can see I have written xq. So your error will lie between minus del by 2 to del by 2. Why I am identifying all these things? Because I need to calculate the quantization noise power. Because what is the quantization error? This error is also called as noise. And I need to calculate the range so that the total noise power I can calculate, and simply I will divide with respect to the signal power to get SQNR. Okay. So let us consider one case. Let input is 5 volt and your level 2 is around 5.5 volt. Okay, let us consider like this. This is one case. So L2 is around 5.5 volt as it is given, and the input potential is 5 volt. Means input potential is 5 volt, and it falls in the decision boundary D2 and D3, because here it is given that level 2 is having a potential of 5.5. Then so 5 is input and output is 5.5. Okay. Now what is the error? How to calculate error? Error is equals to input minus output. So it is minus 0.5. Then so this is my error. So how much error? It is minus 0.5 variation, because my input is 5 volt, but after quantization it is identifying the level 2, and the level 2 is assigned with a potential 5.5. Okay. So 5.5 is the nearest level, so error is minus 0.5. Then similarly, this is the upper part I am considering. For example, if I am considering this level 1, let us consider this is 4.5. For example, whether it will go to this or this, because there are the two variations are there, level 1 and level 2. So level 2 is 5.5 and level 1 is 4.5. Then so I have considered with respect to level 2. But suppose if it is identifying level 1, that means 4.5 is your output. Now let us consider it is a point falls in level 1. This is falls at level 2. Now it is falls in level output is level 1, 4.5. Now there is also one error. What is that error? Deduct 5 minus 4.5. How much it is? Again it is a 0.5. So if L1 is 4.5 volt, if the output, these all are output. Okay, these all are output. If it is 4.5, it is coming. That means it will fall in level 1. And what is your error? Error is 5 minus 4.5, that is equals to 0.5 volt. Here it is minus 0.5 volt, here it is 0.5 volt. So what it is? The step size remain constant. How much it is? If it is del by 2, this is also minus del by 2. So if you take the step size, this is your 4.5 and this is your 5.5. What is the difference? The difference between this is del. and your step size is around how much potential maximum to minimum? So 5.5 minus 4.5, that is 1, and half distribution is there. So if it is go up, you will face minus potential. If it is goes down, then you will face plus difference. So this is your difference, 0.5 and minus 0.5. Okay, like this analytical question may come in your exam. Now next, we need to calculate SQNR, that is signal to quantization noise ratio. How to calculate SQNR? Now signal power below, quantization error also we have identified. We have identified the range of quantization error. Okay. Now we need to calculate SQNR. For that, as we are identifying the noise power with the help of power spectral density, similarly here we have to calculate with respect to probability density function, because here probability will come into picture. How many number of levels are there? 4 levels. Okay. So what is the equiprobable of this 4 level? 1 by 4, 1 by 4, 1 by 4. If you multiply that 1 by 4 to its strength, you will get the noise component. Okay. So let's see. So quantization error, I am writing quantization error, that is Q, and it lies from minus del by 2 to del by 2 f of Q. This is the function. Okay. And what is the strength of it? 1 by del. This is the strength of this particular function. If you consider this is A, this is B. Okay. So total noise power available in this particular region, you have to calculate. So there is a small calculation. So noise power calculation is N is equals to B square plus A square plus AB divided by 3. Okay. B square means it is minus del by 2 square. A square means it is del by 2 whole square, and AB means minus del by 2 and del by 2 divided by 3. So if you square it, you will get around how much? It is del square by 4 plus del square by 4. This is minus del square by 4 divided by 3. So this one get cancelled out. The noise power will be del square by 12. So this is called quantization noise power, NQ. Okay. Always remember that your quantization noise power is del square by 12. Different books has having different derivations. This is the smallest derivation what I have seen. If it is with respect to probability, then you have to consider the probability density function. There is also one sort of derivation in there that I will also discuss with you. But for the time being, for the simplicity, noise power is available within this particular range. So range is from minus del by 2. So you fix the value, that is B and A within this particular region. So the equation will be B square plus A square plus AB divided by 3, because 3 components are there. And if you solve this, you will get around del square by 12. This is the quantization noise power. Now if the signal power is low, if you divide this component to it, you will get your SQNR value. Okay, let's see. Okay, so our quantization noise power is equals to del square by 12. So what is del? Del, as you can see, del is equals to BH minus VL divided by L whole square divided by 12. Okay, like this I can write. So here I can write VH minus VL whole square divided by 12 into L square. But what is L? L is nothing but 2 to the power n. L is equal to 2 to the power n. So here I can write VH minus VL whole square 2L 2 to the power n whole to the power 2. So this is one relation. So this is called quantization noise power. Now if your higher potential is given, lower potential is given, peak to peak value of a particular signal, you can easily find out the quantization noise power. And that too, if number of levels are given. If number of levels are given, you can directly substitute L square. You can directly substitute the value of L and you can determine your quantization noise power. Okay. So here I can write the quantization noise power is inversely proportional to L square or inversely proportional to 2 to the power 2n. So this indicates what? If the number of binary bits are increasing, if the number of levels are increasing, your quantization noise is reduced. So here I can conclude that quantization noise power decreasing if number of levels are increasing because it is inversely proportional. Similarly, if the number of binary bits also increased, because if the number of binary bits increases, your number of levels is automatically going to increase. Okay, and if the number of levels is going to be increased, your quantization noise power is going to decrease. It is the first case. Second case, if the quantization noise power is increasing, your number of levels is decreasing. If how this number of levels will decrease? If the number of binary bits get decreased. So these are the two cases. Okay. This arrow means it is decreasing, it is increasing, this is also increasing. Okay. This is the number of binary bits. This is bits. This is number of binary bits. So if the quantization noise power is increasing, then your number of level will decrease, number of binary bit is also going to decrease. So these are the certain relations. Okay. Now we will discuss how these potentials are identified with levels and the levels are coded with some sort of binary data. Okay. So that is called sampling, quantizing and coding for analog to digital, for analog signal, you can say, for analog signal. Okay. So first we will sample, then we will quantize, and then we will assign the binary bits to that particular value. With the help of this table, you can understand what this quantization actually happens. This is sample value of signal. Okay. Then nearest quantized value, nearest quantized level. Okay. Then quantizer level potential or voltage, you can say. Okay. And then the binary code 1, let us consider first case is 1.7, this is 2.7, then 3.9 volt, then 5 volt, then 6.2 volt, then 7.2 volt, and then 7.7 volt. Okay, and this is L1, this is L2, this is L3, this is L4, this is L5, this is L6, this is L7. Number of levels, and the quantized potential is 2, because 1.7 nearest potential is 2, 2.7 nearest potential is 3, 3.9 nearest potential is 4, 5 is around 5, 6.2 is 6 volt, 7.2 is 7 volt, 7.7 is around 8 volt, like this, because this is the round off value. If it is above 0.5, it will take the next value. If it is less than 0.5, it will take the lower value, round off value. So you can see the 1.5 is round off to 2. So it is a quantization is done. But it falls in which particular level? It falls in level 1. Similarly, 2.7 is false. 2.7 is greater than 2.5 and it falls in a level 2 and it is assigned as a potential 3 volt. 3.9 nearest value is 4 volt. If it is 5, as it is 5. If it is 6.2, it is 6. 7.2, 7. 7.7 is greater than 0.5 value, so it is 8. Now, here how many number of levels are there? Okay, so here the number of levels are 8. So you need to assign those particular levels with the binary data. So for level 1, since there are 8 levels, how many number of binary bits do we require? The number of binary bits we require is 3 for each level. So for level 1, I will write 0, 0, 1. For level 2, I will write 0, 1, 0. Level 3, 0, 1, 1. Level 4, 1, 0, 0. Level 5, 1, 0, 1. Level 6, 1, 1, 0. Level 7, 1, 1. Simple. So this will identify the potential. So when this binary was represented, that means you have converted the sampled signal into a binary data. This is called conversion of analog signal to the digital signal with the help of quantization process. Okay. So this is the table through which you can understand if the number of levels are there. Each level is assigned with a certain potential. If it is nearest to that level, 1.7 is nearest to the 2 volt, it will consider 2 volt. If it is 2.7, nearest potential is what? 3. If it is 2.2, then the nearest potential is 2. So like that you have to identify the levels. If it is 8 levels are there, even though if it is 6 levels are also there, you have to consider 8 signals, 3 parameters, because 2 to the power 3 you have to consider, so that 8 levels will be there. 2 levels are unused, no problem, but 6 data is available. Your data must be secure. For example, if there are 4 data is there, that means 4 level you have to assign. Okay, if there are 5 output potentials are there, let us consider if it is 1, 2, 3, 4. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. Okay. Now, for example, if there are 5 outputs are there, if there are 5 means 1, 2, 3, 4, 5. If there are 5 outputs are there, then also you have to consider the 8 levels, because we do not to miss any sort of information of a particular signal. It need to be secure. If it is 4, well and good, 4 level is assigned, but if it is greater than 4, means 2 to the power 2 is 4 is the 4 level, but for the 2 to the power 3, 8 levels are there. So for 8 levels, you can transmit 5 data, you can transmit 6 data, you can transmit 7 data, you can transmit 8 data. But if you are transmitting 9 data, that means for 9 number of levels or for the 9 number of data, you have to use 2 to the power 4. 16 level must be there. In order to transmit 9 data, 16 levels you have to create. 16 levels means the rest of the data or rest of the 7 levels will be remain unused, no problem. But the levels will be identified with respect to L is equals to 2 to the power n. It must be satisfied. If it is greater, consider one more number of binary bit. If you are considering one more number of binary bits, means number of level will increase. Okay. So this is the basic relation between sample signal, nearest quantized value, nearest level potential and the binary codes. So once these codes are known, these are available in parallel, but we are transmitting the signal in series. So you have to convert this parallel binary data to series with the help of parallel to series converter. Okay, it will convert the parallel data into the series. And once it is transmitted, those sort of information are called as pulse code modulation, because here pulse are coded with binary data. Pulse are quantized. Quantization means some discrete potential will be available, and quantization level will identify the round-up value, and each level will be assigned with binary data. Binary data is going to be transmitted in a parallel manner. You need to convert that parallel to series. If you have converted parallel to series, that means it is called as a pulse code modulation. Okay. Okay. So this is the type of uniform quantizer. Okay. Uniform quantizer means the step size of that quantization levels, the distance between two levels, or you can say the distance between two decision boundary, if it is remain constant throughout the system. If the step size remain constant throughout the system, then you can say it is called uniform quantization. Okay. If it is uniform quantization, there are two types are there. One is mid-trend and one is mid-rise. Mid-trend and mid-rise follows the same characteristics of uniform quantization with the same step size, but the representation is quite different, just opposite of each other. First, let me discuss. As you can see that the figures are available, this is called mid-trend and this is called mid-rise. Mid-rise means, you can see this is the center point 0. In this center, half of the part of a step size is above this line, half of the step size we have to consider below this reference line. If we are considering the step size in vertical, then it comes under mid-rise. But when you consider this step size as a horizontal, then it becomes as a mid-trend. As you can see, this is the horizontal case, and your step size increases. Okay. The step size remains constant, and the distance between two consecutive positions will be the odd numbers of del by 2, because here the step size is from minus del by 2 to plus del by 2. Here you can see minus del by 2 to plus del by 2. That is one step, remain constant throughout the system. If your del remain constant means it is uniform, but the representation is different. If the step size represented in vertical manner, then it will come under your mid-rise. If it is in vertical manner, the response will be identified with the consecutive position of del, 2 del, 3 del, 4 del with an amplitude of odd number of combination of half of the quantization error. Quantization error is how much? Del by 2. So here you can see when it is del, quantization is del by 2. When it is 2 del, the quantization error is 3 del by 2. When it is 3 del, it is 5 del by 2. Odd number of combinations are there, because you need to satisfy this step size. If I will take a difference between these two, okay, so it is 5 del by 2 and this is 3 del by 2. If you take a difference, it will become as a del, remain constant. Either you go in this particular manner, either you go in this particular manner, in positive half as well as negative half. Same thing. But the thing is what? Your step size remain constant. So here you can see if the step size we are considering with respect to vertical positions, Okay, sometimes you have to consider vertical, sometimes you have to consider horizontal. If you are considering with respect to vertical, then it is called as a mid-rise uniform quantizer. Similarly, if you are considering horizontal, it is vertical, it is horizontal if you are considering, that means odd number of position of del by 2 will have del 2, del 3, del 4, del, it is just opposite of it. Okay, and here also, if you take a difference between two levels, it resultant is your del remain constant. This is the transfer characteristics of a particular system if it is called as a mid-range uniform quantizer. If the transfer function respond to this particular characteristics, then I will say it is called the mid-rise uniform quantizer. Okay, and with respect to this, your quantization error characteristics will be look like this. Here you can see the figures are moving in this particular manner. That means we are moving in this manner. The quantization error in this particular right hand part. But when you consider this vertical part, it is just opposite, because as I have told, if you rotate this one, it will become as a replica, means opposite of this particular value. So once if it is, we are considering the quantization component with respect to this mid-rise uniform, then it is just replication of this particular uniform. So it is the representation of variation of quantization error with respect to input, and these are the two characteristics, two transfer characteristics for uniform quantization. If it is mid-rise, follow these characteristics. If it is a mid-trend, follow these particular characteristics. Okay, so these are the two type of uniform quantization, with the help of whom we can determine the quantization noise. If the quantization noise is known, how many number of levels are there, that also we can identify, as well as our main motive is to determine signal to quantization noise error. Okay, or you can say signal to quantization noise ratio, and the ratio must be greater than 1, so that the quantization error must be less, and round-off value will be, approximation value will be less, so that the error contribution is very less, signal strength will be increased. Okay, so that is our main goal. So this is the type of quantizers.